Hey everybody, welcome to this video about where do steering forces come from. What is this video about? Well, if you're a sim racer or perhaps you're a real racer, you might want to know a bit more about the force you feel through the steering wheel. Where does it come from? Yeah, well, that's all we're going to answer. But there's quite a bit to it. Many different things, and it's for sim racers because, well, I am sort of a sim racer, and recently the direct drive force feedback systems are becoming a bit more affordable. The sim physics engines are advancing, so you can actually compare real life and simulation to each other quite well. So we are going to look at all the major factors that affect the steering forces that you feel, and it doesn't actually matter that much if it's a sim car or a real car. So wherever you're from, it hopefully should be interesting. And of course, this is only for those who think that engineering explained is way too easy and softcore. We hardcore, bro. So what's the plan? There are quite a few things involved here. So I'm trying to do it one thing at a time, and then I hopefully explain that one thing ish. Asterisks, and then we'll load up the simulator and actually demonstrate it and see with the webcam. You can see how the steering wheel reacts and what happens, and I'll try to explain it a bit more about how it feels and what just happened. So hopefully that's a more practical view without just getting too deep into all the spreadsheets and charts. That part probably helps some of the less nerdy ones to see a bit more about what's going on. There are a couple of things that are the major sort of contributing. I did drink a little. Makes my English worse. I was hoping it would get better. A couple of things that really affect your forces through the steering wheel. The weight effects, we'll get to that. Tire forces, of course, a major part. And finally, the suspension forces also play a role in transmitting forces to your steering wheel. So we'll tackle them one by one and see what comes out. The effects of the weight, just the hefty bits. Well, there are rotating masses, and there's also the spinning masses. But let's switch over to sim racer driver Niels and let him explain. So here we are in our very special Mini. So what about these effects of weight? I mean, currently we don't have any rubber effects at all. Steering doesn't center. There's really nothing to feel. There's no force feedback whatsoever. However, there are a couple of things happening. So the suspension doesn't do anything, the tire doesn't do anything, but we still have some effects. Because imagine turning this wheel. Even if the car will be jacked up and the tires would just be hanging in the air, turning like this, you're rotating those front tires. Not spinning them, we'll get to that later, but just turning them. And that's weight, and we know from experience, pushing a shopping trolley around the supermarket, if you want to change direction, it takes a bit of force to change direction. So wiggling the steering, I do feel a little bit resistance, even though there's absolutely no feedback when driving. The wiggle, yeah, it's a little bit. However, if we speed up, we get another effect. That's from the gyroscopic forces. So the tires are spinning, rotating real fast. Not yet, haven't unleashed the special sauce of this Mini, being rear-wheel drive and 200 mph capable. So let's go a bit quicker. Already I feel it loading up. Just wiggling now, I feel actual resistance, and it's a little tricky doing with my fingers. I have to use my hands. That's what she said. So now we are really getting up to speed and wiggling the steering now. It's considerable resistance. It's not super heavy, but you do feel it. Whereas if we now slow down, if this thing manages, the slower we go, the less. Yeah, it's way less now. So it's a speed sensitive thing. So the quicker you go, if you wiggle the steering, once once you're steering at a certain rate, it won't be as noticeable anymore, but especially when you change direction quickly, like catch oversteer at 200 miles an hour, there will be some extra resistance from you wiggling that steering at high speed from the gyroscopic forces. So that's nothing to do with suspension geometry or rubber, but still force feedback. So that's an interesting thing, I'd say. On to the next then, Niels. Back to your PowerPointy nerdy stuff. Thanks, SimRacer Niels guy. So yeah, that was interesting to see, and you may not have expected that, because I think you probably expected some tire effects, and that's the ones we're going to talk about now. When you look at the tire in a top view in this perfect drawing of a racing car, there are a couple of effects. There's cornering forces, the red arrow there, and acceleration and braking forces, which we call longitudinal forces, and the cornering forces we call lateral forces. And I've drawn them here, all acting right in the center of the tire, and well, we're gonna see what happens. There is a huge effect for deciding how heavy your steering wheel feels, and that's called pneumatic trail. And what on earth is that? Well, this lateral force that we just shown, the red arrow, it doesn't actually apply in the center line of the tire, but it applies a little bit behind the center line. That's a little odd, but we'll get to that. And this distance, how far it applies behind the center line of the tire, isn't constant. It really depends a lot on the slip angle of the tire. And this trail, therefore, it starts at its maximum value when you start steering, and the further you steer, the more this trail drops to a distance of 0. But let's get a bit deeper into this. Here we have a side view of a tire, and you can see that we are increasing the load. This is a little load, this is a bit more load, and even more load. And what you can see is that the contact patch will lengthen, of course. It gets bigger, the tire gets flattened a bit more. That makes sense. And you would expect the force, the cornering force, to apply here in the center line of the tire, but it doesn't. The reason is, when you're just starting to steer, this contact patch deforms, and the average point where the force actually sort of is applied has to be somewhere in this contact patch, but based on the deformation it tends to be a little bit behind the center line. So it's a little too complicated to go into super detail, but assume for now that's correct, and that the force can apply a bit behind the tire center line, which is illogical in a way, but also very important. So here we have a top view of this racing car, which somehow had its right front tire ripped off, but just to keep it a bit simpler, there's only one tire. Here we have it drawn at 0 slip angle, so the car is moving forward, and the tires are also pointing forward. So there's not any cornering being done, you're just driving straight on, there's no cornering grip. The slip angle is 0 degrees. And here, this is the trail, this distance between these purple lines. It's maximum now. And then we start to apply some steering, and we get a bit of a slip angle. So the car is still pointing forward, driving forward, but the tires are now pointing slightly to the left. And that difference in angle is what we call the slip angle. And in this case, I've drawn 4 degrees. It's actually more, but this makes it more visible. Now we still have a bit of trail, but it's diminishing because, as we mentioned, the trail is getting less and less the greater the slip angle is. So this trail distance is a little less, but we also have a lateral force now. We didn't have a lateral force here, we weren't even steering, there was no side force, but now we're steering and the contact patch is fighting against the tarmac, and we have a lateral force and some trail. And then we continue to steer, and now we are at, say, 8 degrees slip angle, which is typically an optimum point where your grip maximizes. And at that point, remember, at optimal slip angle we have no trail anymore, so the the pneumatic trail is 0 here. It started out big time, started to reduce a bit once we started steering and get some slip angle, and now that we've arrived at the optimum point where the tire produces its maximum cornering force, we have no pneumatic trail anymore. But we have the maximum cornering force. This arrow has just grown quite a bit. So what can we do with all these points? Well, we can see if we can make a little curve. So let's draw a nice curve here. Here on the x-axis is the slip angle, and here we have 0 slip angle, so we are at this point. We have no lateral force, that's this red dot here, and we have the maximum, just getting rid of some clipping here, the maximum pneumatic trail, which is maximum here. In the next picture, we get a situation where we're sort of halfway through. We have a drop in the pneumatic trail, this distance, smaller, and actually we get some cornering force now. So the lateral force, this red arrow, means we have force. And we do it for the final example where the trail is almost 0 again, and now our force has maximized. Then what we can do is connect the dots. Actually, we need more dots before we can make these detailed curves, but imagine we have more points than just these 3 points, and we actually connect the dots. You get something like this. So slip angle grows, your cornering grip that makes the car go around corners also grows, and that flattens off, and the pneumatic trail drops. That's just some reasonable representation of what most likely happens. Alright, now we have a force and a distance, and I see people yawning in the back of the class, so I'll try to speed this up. Force times distance is torque, and this is what you would get, the self-aligning torque, and that's a very popular, well, I wouldn't say popular, kind of well known. I think you've all heard about self-aligning torque, and this is what it is. It's just a product of pneumatic trail and lateral force, and that results in a self-aligning torque. And this you would feel through the steering wheel, among other things, but purely isolated, this is what you would feel. So you start to steer, you get slip angle, you get a peak in force feedback, and then the force feedback would lower. You would feel less and less resistance as you maximize your tire grip. So what is important here? A lot of the time you hear people talk about self-aligning torque as if it's a standalone thing. It isn't, because it's always the result of force acting at the distance. And that means if, for example, you drive on ice, that means just very low grip, and that's why your self-aligning torque and your force feedback from the tires will be reduced. And if you lock your brakes, that's a situation where you don't have any lateral force anymore because the tire is locked, it doesn't produce any side force anymore. That means you have no self-aligning torque. So tire load, for example, a heavy load on the tire makes the pneumatic trail larger and therefore increases your self-aligning torque. Tire load also increases the potential grip of the tire, further increasing the self-aligning torque. So it cannot be treated as a standalone thing. It's always the consequence of having a certain distance, which is depending on a couple of things, and having a certain lateral force, which also depends on lots of things. So self-aligning torque, really important, but look at it as force acting at a distance. And yeah, we also saw the self-aligning torque drops long before the grip is maximized. That's going to be interesting. So if you trust what you feel through just the self-aligning torque part of the force feedback, you're feeling the steering go light, which is commonly misunderstood for losing grip, but you're possibly still gaining grip if you would steer beyond this point and actually allow the steering to get a bit light. So another few charts here from my spreadsheet. Here we have a tire at a few different loads, because tire load is always hugely important. You can imagine if there's no load, no weight on the tire, it's floating over the track, it cannot provide any grip. So one of the main properties, how much grip can you get from a tire, will be how hard it is pressed onto the road surface. And in this case we have 2000 up to 6000 newtons of tire load. And here we see the trail, that thing that drops as slip angle increases. This is straight from the simulator. And you see every time we add 1000 newton of tire load, we sort of get linear-ish steps up in the pneumatic trail. This won't be 100% accurate, but it's a reasonably good representation of what will happen. There's not that much wrong with it. So that's a linear increase. For every bit of extra tire load, we get a bit of extra pneumatic trail. But the self-aligning torque is a product of the force that grows with tire load and the pneumatic trail that grows with tire load. So here you can see the self-aligning torque grows way more rapidly. The gap between these dotted lines isn't constant as it is here. So self-aligning torque is very sensitive to the tire load. It's quite important for like downforce cars where it can load up very high and you have to work for it at high speed. That's what I just said. So, summarizing this self-aligning torque stuff, how does that create steering force? Well, beautiful drawing time again. Here we have that little bit of slip angle, 4 degrees. So we still have some trail. We also have lateral force. Now imagine that this is the pivot point of the suspension. And this force acts a little distance away from it. We have distance times force gives us a torque. And this is the steering arm, which is connected with a rack and pinion steering system to the steering wheel. And we have, of course, a wheel on this side as well. If you look at what these forces do, on the left tire here, it twists the suspension. It wants to rotate the spindle, the upright, to the left. And on the other side, we get the same. This lateral force causes a moment to the left and pushes the steering rack to the left. And that rotates through the rack and pinion steering, the steering shaft to the left. So if you don't touch it, the steering will move to the left. And in order to avoid this, if you would like that, you'd have to apply a force or a torque the other way. So that's why, that's how you actually get to feel this effect. So this rack and pinion stuff, how it moves over the links in the suspension, the tie rods, and these forces, these moments being countered here. That's how you feel it. But let Niels do the talking. Thanks, Niels, you PowerPoint muppet. Back in the car where the interesting stuff happens. We've enabled self-aligning torque. All the yada yada yep yep that I did. Sorry, that Niels did just yet. Let's just show what it does. I have pretty firm resistance now. It doesn't really matter if I go slow or fast. Let's just put it in third gear and drive slowly. So I feel quite a bit of resistance. But, oh, now it gets light and now there's nothing, almost nothing, you see? A tiny little bit remains, but it's almost gone. Everything happens off center. And it ramps up real quick. I think here is about the maximum. Like 45 degrees of lock, perhaps, yeah, ish. And then you feel it start to fall off quickly. And then here is the point where I can use what? Oh, yeah, where's the finger point? No pun intended. Pretty soon, right? So here at 90 degrees we almost have no force feedback left, and the more we steer, the more understeer we get, and it barely manages to self-center. So the self-aligning torque here, you really feel that ramp up very quickly. But extremely, extremely, extremely important is, don't mistake if you would feel just this, there are many other things that we will feel later. If you are only to feel the self-aligning torque, and you feel the steering go light, you're not at maximum grip yet. It takes a little more steering. Can we demonstrate? Well, there are circles here, let's see. Let's take this at the speed where it starts to go light. It's about here-ish. So we're doing 50-ish miles an hour on the speedo. And now it feels like understeer, but I'm actually turning tighter. So let's go back to like 50 miles an hour. We're at about the heaviest point of steering, following that line. And now, if I steer, you see, there's way more grip available, even though I feel nothing. So the steering going light has nothing to do with your grip disappearing at all. Now, it might still happen like that when we add in all the other stuff, but just the tires force feedback part, the self-aligning torque, most of your force feedback is gone by the time you hit maximum grip. So don't mistake a lighter going steering necessarily for loss of front end grip. It's not necessarily true. Really interesting that. Now back to you, you boring muppet. What? Jeez, this guy has got some nerve. Anyway, that's hopefully insightful how that works and how the pneumatic trail and self-aligning torque adds up. The next effect we'll talk about are suspension effects. So the tire is pretty much dealt with now, but the suspension also has many ways in which it can add to or subtract from the forces you feel from the steering. The trail we just talked about was pneumatic trail, but there is also a possibility to add some suspension trail in it. And here we can kind of see how that works. So without suspension trail, we were at the maximum slip angle where the grip is maximized. That's where you want to be, of course. We saw that we had no self-aligning torque because we had no pneumatic trail anymore. So here you feel absolutely nothing through the steering wheel. Now add some suspension trail, which I've done here effectively by moving the tire backwards towards the middle of the car. Now there is some trail left, even when we are at 8° slip angle and the tire has no pneumatic trail. By adding some trail in the suspension, we still get this moment here and the forces that pull on the steering rack, and you feel that through the steering. So that's the first sort of suspension effect that we'll look at. And how does that sort of add up? Well, we saw the charts earlier of the self-aligning torque. Imagine adding a little bit of trail. This line that we had earlier, which was just the pneumatic trail, which started at a certain value and almost reached 0. If we add some suspension trail, effectively this shifts up. So we start even higher, there's more trail because we have the pneumatic trail plus the suspension trail. And even when we maximize the slip angle to get maximum steering force, there is still that suspension trail left, which is the distance here from 0 to there. And that changes the shape of this self-aligning torque curve, which now includes the trail of the suspension. So remember how light it got. I could steer with one finger once we were past the optimum, once we are at optimum grip and a little bit beyond the peak of the self-aligning torque, I could steer with one finger. And now by adding a bit of suspension trail, I can no longer do that because the force, it drops a little, but it's still fairly heavy. And if you go even more extreme, adding more trail to the suspension, which will be very hard to physically do, especially in racing cars with slicks and downforce, but let's say you keep adding it, so you offset this trail line even more, then the force will ramp up very quickly and barely drop off. So it's very heavy force all the way up to maximum grip at the lateral force peak here. Now let's have a look in the sim how that all pans out. So here again in this marvelous little vehicle with self-aligning torque and now with some suspension trail. So remember what happened, if we turn tightly the wheel will go super light, but now we have extra trail, so there is extra twisting force in those front suspension. It tries to tug, pull on the steering arms and turn those front wheels. So if I have that understeer now and let go, you see it's very snappy back to center. Even when we have way much understeer, it still centers very quickly. Whereas before, without that mechanical trail that we added, it would just almost stay there and it would barely return to center. And now it's snappy, there it is. And the steering, I still think it gets like around 60 degrees. We've reached the maximum. 45, 60, and now it gets a little lighter, but it sort of stays constant. This is of course way better to drive because the steering actually remains firm and you know what it's gonna do and you feel some centering force. So that's the effect of suspension trail added. Back to you. Running out of insults. Mr. Heusinkveld, take it away, man. Thanks, Niels. You're getting kinder every video. I like that. The next part to talk about is the scrub radius. So going back to this top view of the car, we can quite easily see what happens if we have a longitudinal force. So we're done with the lateral forces. Now we're doing longitudinal forces, so braking or acceleration. Now looking at the front tires, acceleration forces can only come if you have a front-wheel drive car. But let's see here, we have top view. The scrub radius is the distance between, in this case, this really simple suspension, the pivot point of the suspension and the center of the tire. So if we have a braking force here, we are braking equally left and right, we get a force here and a force on the other tire. And if you look what happens, this force tugs the tire rod to the left and this force forces the tire rod to the right. But the net effect of that, the sum of that is zero. So you don't feel anything when you brake and the left and right brake function the same and the tires are the same. And of course this is typically true. You don't feel anything here. But now what happens if the loading is asymmetrical? So for example, this tire on the right is on dirt or oil or ice, and the tire on the left is braking on asphalt. If you apply the brakes now, the left tire, being on a much better surface, can provide a lot more braking grip than the right tire. So you can see by the size of these arrows that it is tugged to the left far harder than it is tugged to the right. So even though these are no steering forces, or the loads that are applied to the tire are longitudinal, you would say that has nothing to do with steering, we still get a leftward torque here because this force creates a bigger rotational moment torque here than the countering one. So the net effect is that the steering rack wants to move to the left and the steering wheel wants to move to the left. And we can also demonstrate this, well, when I say we, the wise guy Niels, who is about to show us in the sim, hopefully. Yeah, there he is. What have we done? We've installed some scrub radius on the front tires. And we've also seen that typically that reacts more to longitudinal forces, acceleration or braking. Now currently we are driving the special rear-wheel drive Mini, but what I've done is I've busted the right front brake, so it doesn't work anymore. All I have is the left front brake. So what I would expect is there is a braking force there that wants to, because of the scrub radius, pull on that suspension and yank the steering to the left. So if I brake, see, there we go, if I brake hard, that's amazing, isn't it? So these longitudinal forces, which are currently not symmetrical, now I've simulated the busted right front brake, but imagine that tire being on less grippy surface and you have a front wheel drive car and you floor it, the side with more grip will pull harder on the suspension, and if you have scrub radius, it's really proportional to the braking force. And you feel it, like if I wanna, oh yeah. The harder I brake, the more it pulls on the suspension. This is really cool. And you know, what could happen, especially with front wheel drive cars, although yeah, they would typically not be designed I've removed the bright observer will have noticed. I removed the trail again because I want to isolate things. That's what we do here. Each thing shown one by one. But there's very light steering again because there's no trail, just self-aligning torque, so heavy off-center, but braking turns it left. Other situations, what might you see? Well, tire wear could be different left and right, so if you brake, perhaps one of the two tires has slightly higher force and you will get slight twistiness in the steering, pulling the steering a bit left and right. Front wheel drive, as we mentioned, different surface grip on left and right side. It can all pull on the suspension, and that's quite interesting. So longitudinal force, scrub radius, one busted brake, and your steering is proportional to your braking force. And it stays on if I have the brake pressed. So it's light until I brake and then it will go to full lock. Really cool this, isn't it? I think so, Niels. Back to So what about negative scrub radius? Everybody was screaming at me. Well, perhaps one of you. So positive scrub radius. On the left front, here we have the hinge. Here's the tire. I brake and it pulls, it rotates the spindle and it pulls on the steering. If we change that, which is not impossible, a little tricky. So instead of here being the suspension pivot and here the tire, we somehow switch it around, which we can in the simulator because it's all not physically attached. What do you expect? Well, the force pulls that way, steering should pull to the right. Will it do it? Yep, it sure does. Negative scrub radius. And what's the point of all this? Well, perhaps front wheel drive cars, you don't want any scrub radius, or you can decide what you want. Coming out of a turn and stamping on the throttle, do you want that extra driving force on the outside tire to help steering or to make steering lighter? There are some design choices you can make when designing a front wheel drive racing car. Really interesting stuff. Neat, right? Very neat. So that's all good and well, but there is still more to do, more to look at, and let's go all the way, and there are a couple of more things. We've seen trail, we've seen scrub radius, but there are also angles, caster, sorry, I have to burp. The professional video. Caster angle and kingpin inclination. They are angles that are currently zero. So this is an example suspension. Let's look at this thing from my spreadsheet here. This is a top view. So the blue line here is the tie rod, the steering rod. And then we have the green and red are the lower wishbone. And the yellow and purple is the upper wishbone, looking from above. At the front view, there are parallel wishbones and the steering arm is here. And this is a side view. We have the lower wishbone, the upper one, and this is all like a zero suspension. We have no caster, no kingpin, no scrub radius, no trail. This is very square, and no car is actually like this, but this helps you to isolate things, and this is what we used to get the feeling and make the videos earlier, isolating each thing. But let's go a step further. Now we've added some caster and kingpin inclination. We can see the caster, go back. Whew. We can see the caster is 11 degrees, the kingpin angle is about 9.5 degrees. We still don't have scrub radius and trail though, because look at these angles in the front view. This is the kingpin angle, so looking in the front view of the car, continuing the line from the upper ball joint here to the lower ball joint down to the ground. That's this line, with the dotted line hitting the ground. It hits the ground here right at the center of the tire, right in the middle. And that means we have zero scrub radius. So we have the kingpin angle, and where it hits the ground and looking at the center of the tire, the difference there is my scrub radius. So we can have the angle and still have no... That's my phone. Go to bed, somebody should say, but they don't. So I'll continue. Where that line intersects the ground and where the tire is in relation. In the side view here, we have caster. That's probably a little bit more known because you can typically change that in race sims as well. It's again a continuation, the upper ball joint, the lower ball joint, and you draw a line through that and continue it down to the ground. And in this case, it hits the ground exactly at the center of the tire, so we have no trail. But we do have the angles. So that's an interesting thing, because a lot of the time you would mistake caster with trail and perhaps scrub radius with KPI if you're a little bit more into this stuff. But they don't have to exist together. Typically though they do. So here is the suspension that's all the way, and it looks a little bit more like a suspension you would see. Here we have a caster angle of 6 degrees, so in the side view it's a bit less extreme. But by moving these points forward and backward, we have now created a situation where if we extend this line down to the ground, this dotted line hits the ground a little bit in front of the zero of the center of the tire. So there is a little bit of trail there. In this case it's 16 millimeters. Doesn't sound like a lot, but it's actually, you would definitely feel that. And in the frontal view we have the kingpin angle of 10 degrees here, and you can see it hits the ground, if you continue that line from the upper to the lower ball joint, slightly in front of the middle of the tire. So we have a 9 millimeter scrub radius here. Now this is just one of a billion possible suspensions that you can draw and make, and it's very hard to make any conclusions about how it should be, what's best and what not, but just a combination of all the things we talked about, all the suspension effects, made a bit more visible here. And let's do some karting, because they have such weird suspension. Well, they don't have suspension, but the steering geometry with caster and kingpin and scrub radius. So over to you, sim racer Niels boy. So here we have the little go-kart. Extremely suitable things for complaining. What? Explaining, that's the one. Caster, whatever you want to call it. If we look at this thing from the side, let me just drive a tiny little bit. So there we are. You see how the tire swings front and back. That's because of the scrub radius. So here it hinges. It's actually graphically a little bit weird, but you see it hinges there and it swings back and front. And since this is now at an angle, quite a serious angle we can say, about 20 degrees, it sort of moves diagonally like that. So when I steer here, this side moves down, and when I steer the other way, this front wheel moves up. So we sort of twist the whole kart, and the inside pushes down really hard and pushes the whole thing up. So if we go back, yeah, here, I'm standing still now, but it takes quite a bit of force just to steer, because I'm pushing the whole kart up. So it wants to center. And it's quite a serious effect here. It's really not easy to do. Now, a kart is the most extreme example, because you get the most effect if you combine the scrub radius with the caster angle, because then it swings more and it swings downward more. So you see it twisting the whole kart, and I'm actually lifting the thing with the force feedback. So that's a pretty strong effect. And most cars, they have an element of caster. And imagine having like a GT3 car that's 1300 kilos. Now they have power steering, but just jacking the car up, as you can say, jacking forces, I'm lifting it up with my bare hands. That's going to be quite heavy. Imagine a downforce car, where the downforce resists this trying to push it upward. So caster is a very, very serious part of force feedback in real cars, in sim cars as well, just because of you, with some scrub radius especially, jacking the car up and gravity says no, so that's pretty tough. So the kart is a good demonstration of how that works. Yeah, thank you very much, Niels. I'd like to add something though to that. The caster angle alone is not doing all that much. It's the combination with the scrub radius that really causes some serious jacking. But like I also said, you don't need a lot of jacking, like vertical movement, in order to really add some weight to the steering. So caster alone, I'm pretty sure you could make a suspension geometry where you have some caster, but that doesn't really add to the steering forces all that much. But the combination here in the kart with the scrub radius really is the most extreme example. But on average, yeah, caster causes a little bit of lift, like vertical lift of and twist of the car, and changing the tire loads, and you support those tire loads with your hands, and that can get really heavy. So we saw that the caster and the trail, they are angles and they're not the same, but sorry, the caster and trail, yeah, I'm falling asleep here. It's 2 a.m. I've been doing this for way too long. So with the caster is the angle in the side view, and the trail is the distance between the center of the tire and where that intersection of the upper and lower ball joint hits the ground. They are not the same, but typically if you change the caster, those pickup points on suspension, and you continue that line, you will also affect the trail. Same for the kingpin inclination and the scrub radius. They are not the same, but often if you change the mounting points of the suspension, you will change the kingpin inclination, and if you continue that line to the ground, you will also change the scrub radius. So everything combined, and that's where the complication is. We've isolated things quite reasonably well, I hope, and hopefully it was somewhat educational, but the combination of everything is what happens when you drive your car on the racetrack. So the suspension geometry, it really creates complicated 3D rotation of the tire and the suspension, movement of the contact patch, movement of the whole car up and down. You know, there's a lot of stuff going on, and that all affects the jacking. The tire loads affect the forces, and the self-aligning torque changes from the slip angles, and yada yada yada. That's a good summary, I think, here. Let's see if Niels can add anything more in the final video about this whole shebang. So, allow me to summarize a whole bunch of stuff that we just talked about. All the components, force feedback, we saw that. Just jiggling the wheel, the faster you go from the spinning tires actually might add a significant amount of force to your force feedback. But only the quicker you go and the quicker you jiggle the steering, the more that effect is. So a lot of the time you don't really feel that. Self-aligning torque, very big effect. That the steering gets heavier and then drops off. Very big effect, quite major. Trail, further sort of pneumatic trail we had with the tires, mechanical trail, making sure the steering returns to center even if you're way in understeer and the self-aligning torque is almost zero. So that's important. Scrub radius, we saw how that could affect the car, how make it pull to the left or the right if your left and right brakes weren't working quite the same, or if you're making a front-wheel drive racing car, which will have power applied to the outside and inside tires, and if they have different grip levels or have different load on them, they tug and pull on the steering arms, and you feel that in the suspension. We saw with the example using the go-kart, the jacking forces when you steer, and there is caster and some scrub radius, and the car lifts a bit, changes its weight distribution a little bit over its tires. That all has an influence, and I probably forgot about certain things, but those are just some of the major ones. That makes it really difficult now that I'm driving here. What am I feeling? Everything. But can I distinguish what I'm feeling now? No, it's just a combination of everything. Yes, it builds up nicely, it gets a little lighter, and even with this car, it gets a little lighter, but I don't know where my grip is. It's still building up, the force feedback is still building up, Now it's sort of level, but perhaps here is my optimum grip. I just have to get a feel for where that is and look at telemetry. I'm pretty sure I see the horizon go by a little quicker. So this is where the steering is heaviest. I'm pretty sure I have a bit of extra grip if I steer a little bit beyond where the steering goes light. But it'll be different for each car depending on the geometry and all the parameters that we talked about. So you cannot even, like, there's no rule of thumb for if the steering goes light then this is going on. So that's super important, and you just cannot feel that through the steering, even though you may think you do. What else can't you feel? Well, some sim racers, they get a bit carried away and they think they feel everything. Bumps, for example. You always have to go back to the hardcore basics of what you feel and what you don't feel. Vertical forces, you might not feel. I mean, there are instances when you get really complicated. If you have some bump steer and you have a bump and the wheel not only goes up but also turns a little, then we're back to the jiggly wheel bits. Anything that makes your tire, which is heavy, turn a little bit, yeah. So even a vertical force from a bump, if there is bump steer and your front tire moves a little bit, you might feel that, but most of the time you won't. However, like a big bump, like a speed bump, if you hit it with one tire, you might get as if that tire is braking, a little bit of a back force there. That might tug on your car. But things like curbstones and stuff, a lot of the time don't really get transmitted all that harshly into the steering rack. Now the whole car shakes and you feel that, but it's not pulling or pushing on the steering arms and you don't necessarily feel it a huge amount. Slight vibration, but it might just be the whole car vibrating. So you have to be really careful what you say you can feel and what you cannot feel. So now that we're just driving, it's quite intuitive, because I know what will happen and what the steering does. That's just experience, but I cannot distinguish the suspension trail from the pneumatic trail, from the self-aligning torque. Things that are obvious is if I lock the brakes now, it gets very light. Oh, and there it tightens up again. And why is that? Because when we lock the tires, they have no lateral grip. And we saw that a great part of the force feedback came from lateral grip. And what about self-aligning torque? That is a function of the lateral grip multiplied by that little distance, the trail distance. So if you take the lateral force away, which you do by locking the tire, the steering goes light. So that's definitely feedback that you get. And the more braking you have, the more braking forces eat away from the cornering forces. You will possibly feel when you're approaching like the limit of braking, it might be that your steering gets ever so slightly lighter. However, when you're braking, you're putting more load on the fronts. And more load on the fronts means it has theoretically a bit more grip than with light load on the front. So perhaps the force feedback is still loading up, even though you're braking and you're about to lock the tires up, but you might not even feel that because the force feedback gets heavier from the extra load you're putting on the front tires from braking harder. So just to show you how complicated it is to actually talk about what you feel through the steering wheel, because there is so much going on, and it's something that sim racers sometimes overestimate, that they think they can feel when the cup of tea is done or when it's time to go for a shave or something. Certain things you just don't feel. Certain things you do feel. I just showed the lockup of brakes, that's very obvious. And also understeer and oversteer. I mentioned understeer, you don't really know when it's happening, if the steering goes light or not, but you sometimes can feel oversteer, because oversteer is when the back starts to slide. The back and the front of the car, a lot of people, real drivers and sim racers, sort of treat the car as if it's made out of two different parts, but it's not like a bendy bus, which is actually made of two different parts. A racing car isn't. It's firmly held together, hopefully, anyway. So when you get oversteer, the whole car starts to slide. So those slip angles that we talked about will change, and that might change your force feedback. So if you keep your steering wheel here, and we get not enough power in this car. And we get oversteer. My steering goes a bit lighter because there is that slip angle, and the more slip angle you have, the less you feel that self-aligning torque. So perhaps I'm still feeling some self-aligning torque, and then the back steps out, the whole car turns, the slip angle of the front tires increases, and therefore my force feedback is a bit reduced with oversteer. But just, you know, I could go on for days and days. It's just not super simple, but hopefully with this video, by isolating the important parts and explaining them hopefully in a somewhat concise manner, and with this conclusion, you have some idea of what happens, what makes your force feedback wheel or your steering wheel in your real race car, how does it come up with these forces that it's throwing at you, what do they consist of. I'm sure I've left out things and I've forgotten things, but I've spent most of today on this video already, so I'm just gonna put it together and put it out there. Leave your questions down below if you want, and if I made any mistakes, of course I'm eager to know. Post your questions, and I hope you found this enjoyable, and if you ever hear people making claims about force feedback that you think are a bit dubious, show them this video and perhaps they might learn a thing or two. But the most important part about force feedback, and especially in sim racing, is just how far it's come, how good the simulation software is, even though I'm running this skid pad track that is a R Factor 1 conversion from 2007, so no direct X12 here. But the realism in the physics, and in these new force feedback systems that are more and more affordable, the direct drive wheels, it's just amazing. You can really play with the cars. And I've shown how just detailed and correct. Oh, nice. The physics engines are. Oh, and then we're. Yeah. All the stuff that goes on in the physics engine, and you feel it through the wheel. And it's a few €1,000, and you have the sim setup like I have here. It's amazing how far that has come over all the years. So that's why I felt it was probably a good time to make this video, now that this stuff is available to more and more people. And you can actually feel something, unlike the more entry-level force feedback wheels, which are a great way to get started, but you barely feel anything. And with these things, it's a whole different ball game. So amazing times for sim racing. I hope you find this video enjoyable and educational, and we'll see you later. Bye-bye. Well, he just had to show his face there, didn't he? Anyway, guys, yeah, that does sum it up, hopefully reasonably well. Just repeating myself that it's a bit late, and I'm just going with it now, and I'm probably going to wake up in the next morning thinking of all the stuff I forgot. But anyway, I hope it was informative, and I'm out of here, guys. See you later. Bye bye. Thanks for watching. Arrivederci.